So, is it going to be best if I sit here? I guess so, yeah. So, we're going to talk about a couple of aspects, basically. So, I like to call this a full color portrait of the universe, because we can see the universe in many different colors, so at different wavelengths. And we're going to take a look specifically at how we study the evolution of galaxies and the black holes that are sitting at the centers of most galaxies. But more specifically, we're going to look at two aspects. One, how do you bring together and make sense of data taken at different wavelengths with different telescopes for the same astronomical object, which I call data fusion, and how machine learning is increasingly becoming helpful to deal with some of the big data challenges that data fusion and in general, I mean, the studies of the universe going forward, I mean, in this era of big data. So this is our current picture, or a good approximation of the current picture of how the universe came about. So from a very hot and rapid Big Bang and inflationary period at the beginning of the universe, some 13.8 billion years ago or so. The universe proceeded, I mean, to form the first galaxies, and then underwent a rapid increase of the star formation, so the formation of new stars in galaxies, which between a redshift of 3 and 1, if you want to express it in terms of redshift, developed, I mean, the vast majority of the mass that we currently see in galaxies. So the mass that we currently see in normal galaxies at low redshifts, I mean, these nice spirals and ellipticas, most of the stellar mass that we observe in galaxies formed during, between redshift 3 and 1. This is often called, I mean, cosmic noon, and that's the era of the universe where, starbursts and active galactic nuclei occurred, so that a significant fraction of the star formation took place in contexts where there was either a dust torus in an AGN, or a dust shell of surrounding the star-forming regions. So intrinsically, the star formation is a messy, obscured affair. Which means that we got to be smarter at using the different wavelengths of the electromagnetic spectrum to study star formation and AGN accretion in principle. Now, of course, the problem is that if you wanted to track the study of galaxies from the present day to the distant universe, you need to compare, you need to be able to compare, I mean, galaxies at different times and with very different resolutions. For instance, this is what a galaxy this is what the Milky Way would look like if we could take a look at it from top. And this is what some of our nearby galaxies look like in our images. So nice, very distinct spiral arms. Whereas, I mean, when you take a look at distant galaxies, the vast majority of them are just, point-like sources, very distant, and only very few of them are resolved, even in some of the best space-based images, such as the Hubble Deep Field in this case. Participants can now see my screen. That's great. So the problem is, how do you compare, I mean, the properties of the galaxies that you see in the nearby universe with the properties that you observe in the distant universe? And can you make, I mean, a sensible comparison, since, I mean, you have lots of detail, but only a few galaxies in the nearby universe, and many galaxies only sporadically resolved in the distant universe. There is no one-size-fits-all solution, but one way, I mean, to make sense of the properties of galaxies, even when they show up only as a point in your images, is to look at them in a panchromatic manner, so at all colors. This is a project that we worked upon 10 years ago, to combine data at different wavelengths for the nearby spiral galaxy Andromeda. So the message is that, we can take a look at the different images. The X-rays in particular are interesting because you can see that the black hole sitting at the center of Andromeda is contributing most of the X-ray emission, whereas, I mean, the bulk of the star formation is happening in the spiral arms, and those are most directly reflected in the infrared. Interestingly, I don't have radio here. That's because, I mean, I'm not a radio astronomer by background. I mean, I only learned about radio astronomy on the job, I mean, since I came over to South Africa. So the general idea is that the galaxy luminosity, so the amount of emission that they give out, I mean, as a function of time, I mean, how bright, how luminous they are, can be used to trace the star formation rate under some assumptions. So if you can measure the brightness of a galaxy and you can also measure the redshift, you can derive their luminosity. And as it turns out, I mean, people have been using luminosity at different wavelengths, from the UV to the infrared to the radio, to trace the star formation rate. The problem is that whenever dust is present, and when you have this large infrared emission patterns, dust is almost invariably very abundant. You need to be able to correct for the dust obscuration, which basically means that the light that comes to you, I mean, will have been absorbed and then re-emitted in a different part of the spectrum by the intervening dust, the dust that is sitting between the galaxy and yourself, or that is actually part of the galaxy itself. For instance, in this case, I mean, the emission in the infrared is due to bright young stars that are forming and emitting ultraviolet radiation inside the galaxy, well, inside the dust lanes. Then the dust absorbs the UV light. The UV light gets absorbed and gets re-emitted at infrared wavelengths. Over the course of time, so lots of people have used infrared as an excellent proxy for the star formation rate, but lately, well, also because we know that there is a very strong correlation between the far infrared and the radio luminosities, lately radio studies, I mean, have become more and more sensitive to star formation, so that they are about to become superior, I mean, to infrared studies for these specific purposes. Now, how do we measure the broadband spectral energy distribution of a galaxy? We measure it by taking, I mean, lots of observations in different bands, and then we can model it with a combination of different physical characteristics of the galaxy, like, I mean, the number of stars that form as a function of time, the spectra of individual galaxies, and this is well, these are theoretical models, if you like, of galaxy evolution. But the general idea is that when you combine, I mean, the many billions of stars that make up a galaxy, you get an emission that is that often peaks in the ultraviolet. Whenever you overlay dust on top of this young stellar emission, you see that the light is emitted and then shifted in general, I mean, toward the infrared part of the spectrum. And this is done, I mean, in computer simulations, but of course we need multi-wavelength observations in order to see if this is actually what is observed and how well our computer simulations work in practice. So what we do in with tools for SED fitting is to measure, to use different telescopes to observe from the ultraviolet here to the infrared here. So all of these data points are observations taken very often by a different telescope. It can be from space, from the ground, different observations taken at different times. So you put them all together, you have to estimate, I mean, some sensible errors on your fluxes. That is often very difficult. And then you can overlay, I mean, physical models of galaxy emission in order to measure the amount of stellar mass, the amount of star formation that is going on, the amount of dust that is that is lurking at the center of galaxies. So this effect, this shift toward the red part of the spectrum, I mean, due to dust absorption, is combined by another effect, the effect of the cosmological redshift. So as we know, I mean, the universe is constantly expanding. So galaxy, well, any point in the universe is getting farther away from any other point with an approximately, I mean, constant velocity. And this creates the effect of the cosmological redshift. So the problem is that when you observe a galaxy like this spectrum here in red in the local universe, you can use some of the classic optical bands. These are UGRIZ, that are the common bands that one uses for ground-based observations, and you can see that they stretch in the visible part of the spectrum. Now, of course, when you cannot obtain a spectrum of the galaxy, you cannot measure the redshift exactly. You can try and fit the SED shape of the galaxy only based on the integrated photometry that you observe within the individual bands. And this can work, of course, as long as you have emission, as long as you have observations in the bands that the spectrum of the individual galaxy covers. But what happens if this galaxy is at higher redshift, for instance? Then you will quickly see this intrinsically red galaxy moving out of the visible wavelength range, and another blue galaxy at high redshift appearing within the visible redshift range. But what's happening to this galaxy at high redshift? So this red galaxy at redshift 2 will be completely out of the spectrum of the visible. So you wouldn't be able to observe it at all. So you need to go farther, both in to go both at lower and higher wavelength. You need lower wavelengths in order to observe, the bluest galaxies more close, to us, and you need to go toward the red part of the spectrum, toward longer wavelengths in order to measure the redshifts and in general the properties of the spectral energy distribution of galaxies at high redshifts. So one does that, by combining a bunch of filters. There should be a link here, but these are basically filters taken from, UV space mission, ground-based surveys, ground-based surveys in the infrared, space-based surveys in the mid-infrared, space-based surveys in the far infrared, in the sub-millimeter. So this stretches from something like 0.1 micron, so 100 nanometer, to about 1 millimeter and more. And the spectrum that I show here is the classical spectrum of a starburst galaxy. So a galaxy that is forming a large quantity of stars at the present time. And as you can see, the peak of the rest frame SED is at about 100 micron at redshift 0. But when this gets redshifted, and you get attached 1, 3, and 5, you're moving toward the millimeter part of the spectrum. And also the number of, the wavelengths that you use in order to measure the properties of the lower wavelength shift toward from the optical to the mid-infrared. So in other words, you need all the help you can get, from different wavelengths in order to disentangle the full spectral properties of any object that we see in the universe. Now, the problem is that the optical wavelengths that we are mostly involved with, optical and radio, are the only ones that can be observed from the ground, because they are the only ones that are not affected by the atmosphere. Now, the problem is that galaxies forming from complex molecular clouds and black holes can only be observed in their totality, over multiple wavelengths, by using observatories from space. And this means gamma rays, X-rays, ultraviolet, and infrared. Now, the problem is that, of course, space missions are expensive and risky. So it is much cheaper, to obtain, to put up, an extra optical telescope rather than to build, a space observatory. And an example of this that I am particularly fond of, because I worked on its conception, from the very beginning, it was the Earth Space Observatory that flew some 10 years ago as part of a joint ESA and the NASA mission. It was the largest until recently, with the launch of the JWST telescope operated for astronomy in space. It was 3.5 meters. It was cooled passively, by trying to release the heat that it was producing, so that the temperature of the mirror went down to 70, 90 Kelvin. But the real driver was to try and keep the electronics, the detectors, as cold as possible. And for during its operations, Herschel was the Herschel detectors were probably, I mean, the coldest place in the universe. I mean, according to what we know about the universe. So they went down to, I think, 300 millikelvin, so 0.3 Kelvin above the absolute zero. So Herschel was developed to observe in wavelengths between 100 and 500 micron, and was actively developed to trace the peak of the dust emission that in the rest frame is at about 100 micron, up to redshift of 4 or so. And in so doing, I mean, it provided lots of auxiliary data, I mean, for all sorts of purposes. Now, this is all very well, but the challenge that you face when you observe at large wavelengths is the poor angular resolution. So Herschel was a single dish, so it was only a 4-meter telescope. So if you observe with Hubble, that is a 1.5-meter telescope at 1 micron, you obtain a resolution. Well, you can see tiny details. I mean, in an image that is that is rather small, only a few minutes in size. But when you observe with Herschel, which is much bigger, due to the very large wavelength difference, I mean, you will start seeing, I mean, all the sources being blended with each other. This is this is what, I mean, radio astronomy tries to overcome by doing interferometry, and but this is not something that is practical at the present time, I mean, for infrared observations. So the Herschel was our best attempt to date to fix this problem. So here you can see a combination of some of the best images of the same part of the sky in different wavelengths. And as you, if you take a closer look, I mean, you will see that some of the large bright blobs at long wavelengths, I mean, can be identified in the shorter wavelengths. But the problem is that there are multiple possible identifications, because if you took a look at the original image here, you would see many hundreds of background galaxies that could be misidentified for this galaxy. So this is in essence, I mean, the challenge that data fusion presents to us. So we would like to integrate multiple data sources that represent our knowledge of the same real-world object and into a consistent, accurate, and useful representation. Basically, we wanted to know, I mean, what galaxy, what black hole, I mean, is actually sitting, I mean, at the back of these different images, and we want to be able to to identify the same object in all the different images, to measure a flux from all of them, and then try and measure the physical properties that arise from this flux measurement. So data fusion is a term that comes, I mean, from remote sensing, where you have to combine temperature, humidity, images of Earth, for instance, and so on and so forth. But it is very usefully employed in astronomy as well, because the more we rely, I mean, on different sensors, the more we rely on different telescopes, the more you need an automated way to do this kind of data fusion. Classical challenges that I've already hinted about are the different angular resolution that different images have because of the different sizes of the telescope and the different wavelengths which we observe, which of course translates into different spatial resolution. The spectral resolution might also be an issue. Sometimes we would like to have a very finely detailed spectrum in order to see, I mean, all the individual emission lines, but that's very often not possible, because then you need very high sensitivity to do that. Calibrating the images, so measuring the background, removing the background, and measuring the flux on top of the background is a very different process in the different domains of the electromagnetic spectrum. So you need to be able to do it right if you are to put all of the images on the same flux scale. And increasingly over the last few years, there is a problem with high data rates. It used to be the case that space missions, I mean, we're only able to send to ground, I mean, a very small amount of data, but now with, basically digital camera-like detectors on space telescopes, the amount of data is really limited by the power of the antenna that you have on top of the satellite. So we have increasingly high data rates, for processing and well, to be processed and to be stored. And for ground-based telescopes, this is going to be the main challenge. In the ground, we don't have much problems in transferring the data, but the sheer size of the data, and I will make some examples going forward, is something that we have to tackle now. Now, then, of course, you would like to create data that can be passed upon, I mean, through the generations, put on archives, I mean, with metadata that allow you, I mean, to know where they're coming from, how they were reduced, how they were calibrated, and so on and so forth. And you would like to make them openly accessible so that people can reproduce your results or, more importantly, obtain new results and improve results using the data that you reduced. So as part of these challenges, I mean, to be solved for Herschel, we worked on this European South African project called HELP for Herschel Extragalactic Legacy Project, and we took care of all of these steps. I will quickly go to the end so that this doesn't get me dizzy. So basically, we took maps. We got hold of maps, I mean, from large areas of the sky, I mean, over, well, from different telescopes. We homogenized the way we extract these sources and produce catalogs for all the different images. We created metadata that were homogeneous across the different catalogs, and we created some statistical tools to merge these catalogs together. At the same time, we also used the physical models to measure not only the photometry, so not only how bright these objects were, but also how strong the star formation happening, or how long the black hole accretion happening within each of them was. And we use galaxy formation models to compare against our results, and in a circle, well, in an iterative process, so that we could try and best reproduce, I mean, what our observations gave us in the context of galaxy formation models. One of the end results of this, I mean, at least one of the paramount results, is the general health catalog that covered a relatively small chunk of the sky. If you take a look closely, I mean, you will see that it amounts, I mean, to a few percent of the sky, maybe 3%. And these are areas that have been studied all over, well, the history of modern astronomy over the past 20, 30 years, so that observations of many different wavelengths have become available. And we combine, I mean, data for objects that were detected in these over these fields, and we compiled an homogeneous catalog of 170 million objects, which might seem large, but in the big scheme of things, I mean, is not really large anymore. And this is because, I mean, we focused on very specific fields, I mean, where we had an homogeneous way to select sources, where we could create an homogeneous selection function. And at the end of the day, I mean, we brought together 51 different surveys over 23 sky fields, all of them, I mean, with subtle differences that we had to homogenize. And the next phase, I mean, when Herschel was completed, I mean, certainly for me professionally, but also in general, was to try and go beyond what the infrared could tell us about star formation, but also about black hole accretion. So Meerkat is in a number of ways, I mean, an ideal successor, I mean, to Herschel, because it probes very deeply, I mean, into both the star forming universe and into the black hole accretion processes. Of course, I mean, you know about Meerkat. It's now been operating by for just about 5 years now. I think it was inaugurated in April, and will be owned and operated by South Africa for 5 years. So here you can see that my slides show their age. So we're still far, I mean, from having to disband Meerkat and from completing, I mean, the next phase, which will be the SKA. As a matter of fact, I mean, we have probably anything between 3 and 5 more years to go, I mean, with Meerkat. But from day one, I mean, it's been producing some spectacular images, also great for press releases. This is how the center of our galaxy looks like. And it's interesting, I mean, and you might have heard from some of the people here within the department that we also have a companion telescope to Meerkat that is observing the optical. It's called Meerlicht, and it's observing the very same patch of the sky at all times that Meerkat is observing. So the idea is that an optical and a radio simultaneous survey of the sky is currently happening. Meerlicht is in Sutherland, whereas Meerkat is in, well, Dieperkerk. But you have a way, I mean, to actually track objects both in the optical and in the radio at the same time, which is important, particularly for rapidly variable objects that a number of us in the department are interested in. Now, of course, Meerkat is already a big data producing engine. I mean, well, Jordan might have told you something about that or others, but things are only going to get worse or better, depending on how you put it. This is a plot by, well, our colleague here, and Russ Taylor, the director of IDEA, and professor here. So where it is shown that after, well, 15 or 20 years at the beginning of the century, where the size of a typical radio data did not increase much. Bear in mind that this is a logarithmic scale, but still, I mean, it only went up by a factor of 10 or 100. Starting with, well, the Jansky Very Large Array in New Mexico, and now with Meerkat and its companion ASCAP in Australia, and through the next few years with the SKA phase 1, the increase is by and large, I mean, logarithmic. So it's sort of a straight line in this logarithmic plot, sorry, exponential. So this creates the need to analyze data in a smarter manner, ideally only say data that is useful and not drowned by noise, and so on and so forth. And similar challenges are now happening in bioinformatics with very large amount of genome sequences that are being obtained routinely, and for Earth observations. I mean, the large amount of satellites that are now in Earth orbit, and the very large amount of mini satellites that are going to be doing everything. I mean, from providing Earth observations to internet service. I mean, create a challenge in terms of data processing. So, in the future, I mean, it's quite unlikely. I mean, that data on its own will yield new discoveries. In that, I mean, you won't be able to take a look at each and every bit of data that is taken, I mean, by observatories. But the scientific advancements will be increasingly due. I mean, well, you will increasingly require advanced computing capabilities. So the talent and the vision of the scientists will still be there, but you will definitely need, I mean, large, powerful machines to transfer, store, process, and visualize the data. And IDEA was set up, I mean, by now, well, almost 8 years ago, I mean, by a consortium, in order to try and tackle some of these challenges on the way to the SKA. So our claim to fame, and something I've been helping out a little bit, and that Jordan is very busy with on a regular basis, is ILIFU, so our data intensive research cloud. I believe you've been accessing it for some of the coursework already. And here I have a quick rundown of the specs. They're definitely not up to date. I mean, we are constantly purchasing the new nodes and refurbish old ones, and try to improve the total specs of our cluster. The general idea is that it is a very flexible environment where you can both run very large jobs in the background, I mean, through an automated script, or take an interactive look at data on your own laptop screen, I mean, connected to the cloud. This is on the left-hand side. I mean, you can take a look at all of the different technologies that have been put in place in order to create the cloud. I mean, mostly they are open technologies, so we don't have to reinvent the wheel. And also, I mean, we can create things that are reproducible and that can be installed, I mean, on other infrastructures around the world. So the idea to federate infrastructures is a very powerful one. But the idea is that most of this complexity is hidden from the user, or at the very least, I mean, you only need to get to grips with them, I mean, if you are a very advanced user. So most of the action is actually happening, I mean, through Slurm, so through this queuing system with which you can SSH into the head node and launch jobs that are then queued and processed. As soon as some compute is available on the machine, or with it to a lesser scale, on Jupyter Lab, which is probably what you've been using for most of the assignments. So you can create your own virtual machine. Usually the smaller the better, so that you don't hog resources for a very long time, and you can get going with your data, even if it is a very large one in the cloud. Now, how does this affect radio astronomy going forward? This is a picture of what radio galaxies look like in an old survey carried out with the VLSS. Is that the VLA, or is that a sister telescope? Oh, well, anyway, it was carried out by the National Radio Astronomical Observatory in the US, and this shows you the classical shapes of very bright radio galaxies. Now, the main discovery is that they don't look like ellipticals or spirals like in the optical, but they look very often with multiple components. Very often they look like they got tails, or they look very diffuse. They have some large plumes or jets emanating from the center. Now, the problem is that these images span a very large chunk of the sky, so the optical or infrared counterpart is very difficult to determine unless you already have some information about the properties of the individual galaxy. And of course, radio sources are beautiful, exceedingly interesting. The radio flux gives you information about physical properties, and the radio polarization gives you information about the cosmic magnetic fields that are present in galaxies. But the truth of the matter is that the radio spectrum is very often very flat. So if it shifts, it will still be very flat. So you don't have any of that predictive power of observing in different bands and measuring the redshift that you have, with the optical, for instance. So, just to do a quick comparison, you can clearly see that this source, when this source shifts in the radio, you don't have really any way, to tell if it is at a given distance. It could be moved to the right, to the left, and you wouldn't be able to tell the distance. Whereas, if you have a model of the optical spectrum of the galaxy, you can, with a bit of luck and with a large set of training data, with a large set of known galaxies, you can determine their redshift with a reasonable confidence, even if you don't have an actual spectrum to use, but only if you have observations in multiple individual bands integrated over large bands of the optical spectrum. So the properties of radio sources make it somewhat more difficult than usual to study their properties, to characterize their properties, as I put it here. So you always have to tackle these three aspects somewhat together. So you need to detect sources, or you need to detect the peaks of emission in sources, and I believe you'll be doing some source finding tutorials and lectures. You need to be able to identify the multi-wavelength sources that correspond to the radio source, even if the radio source is very extended, even if the radio image has got a poor resolution. And at the end of the day, using the multi-wavelength properties that you determine, you need to be able to classify the source. So is the source compact? Is it diffuse? Is it hosting a powerful star formation, or is it hosting a powerful black hole at its center? All these properties can be gleaned from an attentive use of multi-wavelength data. So again, there are a number of things that one can do in order to solve this radio source characterization problem. So some of the things that keep people busy are: how do you detect different sources, different components in an image, in a radio image? How you can make sense of multiple components of individual sources, of individual radio sources. So when can you tell that two peaks are associated in a single physical source, and when can you not, when can you be sure that those two peaks, are unassociated? Then you need, of course, to be able to generate, little images of the individual sources so that you can compare them, with multi-wavelength data, and you would like the element to be able to do interactive visualization and annotation of the images so that you can take notes on the individual sources. And this is something that IDEA has put a lot of work into through the development of the Carta tool, the Carta visualization tool. I'm not sure you had a chance to look it up, but you might be able to. And then, more and more tasks closer to the science. So you would like to be able to to match catalogs that produced in different wavelengths. You would like to be able to compare the flux in the infrared with the flux in the radio, for instance. You would like to be able to do a detailed spectral energy distribution modeling using physical models. And at the end of the day, we would like to be able to classify the source as one of our favorite classification schemes, whether it is different kinds of AGNs, different kind of star-forming galaxies, or different kind of shapes in galaxies, and so on and so forth. And at the end of it all, the expectation is that you might be able to get on with doing your science, as we like to say in the field. So write a paper, become a prestigious author, and so on and so forth. Now, there's a bunch of things we have tried out over the years on IDEA, on IF. So this is a classic image of a complex radio source that is shown in green with a poor resolution image, and in blue with a higher resolution image. So as you can see, with the poorer resolution image, it's a bit difficult, to make sense of the two components, although you get a feeling that something is double here. When you have the higher resolution radio image, you can at least distinguish the two peaks of emission, but it's only when you put the background image, in this case an optical or infrared image, I forget, that you can put everything in context. So you can see that there are potentially hundreds of background optical and infrared sources that could be the possible match for this source. But an experienced astronomer would be able to tell you that this source, this very bright source sitting at the back there, is the correct match. And this is by a combination of expertise, also by a knowledge of how the jets and the multiple component of radio galaxies shape the appearance of a radio galaxy. And of course, the availability of good multi-wavelength data that you can use to do your multi-wavelength science. Here is a similar example. This is more of an X-shaped galaxy. You can see that in the green image in particular. The blue is not as sensitive, also although it has a higher resolution, so you don't see a lot of this emission that is happening here. And again, an experienced astronomer, after a lot of training, will be able to tell you that this is the correct match. Now, an experienced astronomer, is rare. And it takes a lot of work. For anybody to go through lots of examples of these bright galaxies. So ideally, we would like to be able to do without the expert astronomers. So we would like to be able to generate algorithms that can sort of learn from our experience distilled in lots of papers and like. Of course, in order to assemble this knowledge base, you need some kind of head start, and we created a little graphical interface that one can click and the one can click on in order to generate the correct list of matches. For a number of sources, and this was done by a postdoc working with us. So the general idea is that you can take a look at the overall environment of a source, and then you can zoom in, so you can see if there are other blobs that belong to the same source. But then you go ahead, you take a look at at the source more in detail, and you can sort of see, I mean, how many components it's got, and you can usually pinpoint, I mean, the center of the radio emission, as in this case here. So by doing a lot of these classifications, you not only produce a catalog that you can then use for science, because then you have exactly the properties of this source, this optical source to be associated with the properties of the radio source, but you also create a knowledge base that can be used to automate the process by using some smart tool. And something similar happens also for galaxy morphological classification. When data was sparsely available, astronomers used to classify sources with this Hubble tuning fork diagram. Over the years, I mean, with improving resolution, I mean, we started adding different subclasses and the like, but it is still very much a manual process. So you take a look at some galaxies that pick your attention, and you have to make sense of the properties that are very specific to each other. So it is remarkably difficult, I mean, to create a scheme that is going to apply, I mean, to all sources that you can automate. So for a long time, I mean, astronomers have been working on catalogs of galaxies. I mean, you can find some in the library. So the 1,000 brightest galaxies on the sky have been imaged with photographic plates, and people actually published their images in very large formats so that people could actually inspect them and try and come up, I mean, with their favorite interpretation of what was happening on galaxies. Now, of course, now we've got much better tools, and this is an example of where creating a knowledge base and associating it with some powerful machine learning tool comes to the rescue. There was and there still is, I mean, a project known as Galaxy Zoo that allows people, I mean, from all walks of life, I mean, to play with satellite data or with ground-based data for that matter. Click on your favorite ones and provide, I mean, scientists with answers to some simple questions such as: does this galaxy look a spiral? Does this galaxy seem to be distorted? Does it seem to be irregular? And so on and so forth. So almost 10 years ago, the Galaxy Zoo project came to the stage where it had assembled, I mean, enough classifications by citizen scientists to be able to train a neural network. So a neural network is, well, we don't have time to go into the details, but it's basically a system to create a number of layers from the input, that is your the images, I mean, to the output, which in this case are the likelihood of classifications, I mean, being as a spiral or as elliptical, and it applies a set of layers that apply different operations, I mean, depending on the kind of problem that you're trying to solve. And by adjusting the weights of the different layers and by making sure that the performance of the network is as good as possible on the training set that the citizen scientists have provided you, you can then apply it to other unseen data with the expectation that the accuracy of the classification will stay the same. And this is, of course, I mean, the very same problem that, well, the internet has created, I mean, with millions of images of, well, cats and dogs or different faces, I mean, face recognition and so on. And this is a process that is very efficient when doing image processing, when doing, I mean, computer vision analysis, and particularly when running on GPUs, which is why, I mean, GPUs have become, I mean, very fashionable in the world of machine learning. Now, a few years ago, with very keen student, I mean, we actually started a very small radio source morphological classification project. As you can see, I mean, we started from a well-known sample of compact and, well, FR1 and FR2s that you probably heard of in the radio astronomy courses, and bent radio galaxies. And here you see an example of the 4 classes. So we had not even 1,000 sources to work with, and but we still well, had a go at it, and well, we achieved well, we produced, I mean, a relatively simple configuration for the neural network, and we managed to create a model that allowed us to classify sources accurately 90+% of the time. This is what is usually used to show the performance of a classification scheme. You have the true label on this side and the predicted label on this side. So anything that sits on the diagonal is basically correctly identified. Anything that is off the diagonal is incorrectly identified. And you then have a specific way to measure the performance of your model, which I will define later as precision, recall, and F1 score. But basically, the closer you get to 100%, the better. And here, I mean, you see that our sample was cherry picked, and probably our model, I mean, was a bit too good to be true. But this was what we obtained. I mean, it was very early days, and probably looking at that, I mean, we would be a bit more careful, I mean, with our statements. But the general idea is that when you have large enough samples, you can try and classify sources in an automated manner and also quantify the accuracy that you achieve. Over the last few years, we have seen a real explosion of interest in machine learning techniques for I think this is specifically for radio source classification. So this is a quick summary that we did for a paper that we published a couple of years ago of different neural networks that have been applied to radio source classification. We created a benchmark that tried, I mean, to implement all of these different models, I mean, published by different authors, and compare them in a homogeneous way. I mean, this is a lot of work because very often people don't provide the full code, or the code is not compatible, cannot run on the very same architecture. So we picked a few, a dozen or so models that we could actually get hold of and reproduce on our own GPU, and we tried to put them to the test on an homogeneous expanded data set. And then we did a bunch of comparisons, like what is the mean accuracy that we achieve. So as you can see here, we achieve at maximum, I mean, an accuracy that is 70% or 75% or so, which is somewhat more realistic, I mean, than the 97% that we got earlier. But more importantly, we can also put a number on the number of floating point operations, so on the number of cores, the computing resources that you need in order to compute this model for any one source. So the size of, the position on the plot here tells you how fast the computer is in classifying a given galaxy. And as you can see, this is often due to the number of parameters that are included in a given model. A neural network is basically a model with several millions of parameters. So usually the larger neural networks with the larger circle size are also the ones that are most computationally demanding. So they require a lot of floating point operations to compute the classification of a single galaxy. And what else? Then we also try to check, I mean, how the accuracy per over the full sample, I mean, ranged as a function of images, number of images per second that we could classify. This was using only a single powerful GPU, specifically tuned for this purpose. So this model known as VGG, I mean, still outperformed all of the others, but it could only, I mean, classify 400 sources per second, which might be a problem if you have to classify billions of sources going forward with the SKA. Of course, I mean, things are going to get better in the meantime, but these are the sort of things that astronomers and data scientists working with astronomers will have to tackle in the future when the SKA comes along. And of course, I mean, you have a way to combine these different classifiers in order to try and find the ideal one. These are the performances of the individual classifiers, ranked from best to lowest. You can also combine them, but when you combine them, interestingly, I mean, some things seem to improve. So this is the performance of the the original model. This is the performance of the best model plus the second best model. But then, I mean, the pattern, I mean, doesn't seem to converge. So basically, just combining effective models, I mean, is not often the best way to go. Very often, you just need to create the perfect model in order to be able to do a good classification. Now, astronomers have, as I mentioned, I mean, I've used citizen scientists over the years for a number of purposes. Somewhat more recently, radio astronomers started doing that with a project that was called unimaginatively Radio Galaxy Zoo. So the idea was to get lots of people, I mean, and to get them to label the observations, to create a training set that you can then use to test, to train and to test a machine learning algorithm. And the way it worked, I mean, I don't think it is available anymore. I think it's been retired, as it were, the project, but there are plenty, I mean, of similar projects. One called the LOFAR Galaxy Zoo, and I think there will soon be one for Meerkat and for ASCAP, so for contemporary observations. So the challenge that is offered to the user is to, well, basically use a slider to move from the radio contours that you see here to the radio contours overlaid on an infrared image. And so the questions that you need to ask, I mean, that you can ask users, I mean, must be very simple. So are these 3 bits of emission connected or not? How many do you see? Do you think they are the same object? And when you take a look at the background image, can you see an object that is the true counterpart of this radio source? So something very simple because, well, you cannot expect, I mean, hundreds of thousands of volunteers, I mean, to go through the intricacies of a lengthy astronomy introduction. But people are surprisingly, well, keen to take a look at images. I mean, well, astronomy has got a big fascination. It is often, I mean, very pretty, I mean, to see, I mean, once you have these fluffy sources in the sky. Now, this is a project that we completed with my student Chaka a while back, and where we applied a network that had been trained on Radio Galaxy Zoo data to data of our own. Basically, we used data from the GMRT, which is a telescope in India, and we used the infrared observations by the WISE telescope to produce images, I mean, similar to the ones that were used for Radio Galaxy Zoo, and we used a neural network model trained on Radio Galaxy Zoo data to apply it to unseen, slightly different data. So this is an example of transfer learning. So we are not using quite the same data to apply, to run the neural network, but it achieved, I mean, a very good performance nonetheless. So there is also promise in training neural networks with existing data and trying and apply it to future data. And I think this is an important indication for future observatories and the SK. Now, don't know how we're doing with time. Should we take a few minutes break? Yes. Excellent. So, and yes, if you have any questions in the meantime, let me know now or later. Maybe 5 past and back. Yes. Is that good? Sure. Okay, so have we restarted the recording? Yeah. Thanks, Jordan. Right. So this was all. This was all a bit of a warm up. I mean, for the kind of problems that we tackle in astronomical machine learning scenarios. So some people refer to machine learning as well, letting the data speak for themselves. And in a manner of speaking, I mean, that says it all. I mean, in a little more detail, I mean, the 2 main kinds of machine learning are supervised and unsupervised. I mean, with supervised learning, you either have a knowledge base that you can rely upon, so like a a set of labels that were assigned to galaxies, or a set of images that were classified by people on the internet as cats and dogs. And you can use it for classification and regression analysis. So you can basically use them to classify sources, or you can use to do a regression, so estimating a continuous quantity, whereas classification is by definition a number of discrete values, for a label. Unsupervised machine learning is used when you don't have a truth set, when you don't have, for instance, predefined set of classes, when you don't have a predefined measurement for the property that you're trying to measure. So, and it's usually used to cluster sources in parameter space. So you find different clusters of objects, and then after the fact, you try and figure out, what, how they differ, and if you can assign, these different clusters of sources, some properties based on your astronomical knowledge. So some classic problems that have been tackled with machine learning and astronomy related to classification. For instance, how do you classify an active or active nucleus, or a black hole powered object? How do you classify so a source as a galaxy or as a star? How can you separate these three classes? With a combination of images and catalog parameters. And another classic example of the regression instead is to estimate the photometric redshift estimate. I will go in a little more detail about these two examples later. For clustering and feature extraction, you can think of trying to discover and separate different populations, maybe new populations, so detecting anomalies. So you might be able to measure properties for billions of sources, but you want to focus on the few dozens of sources that are genuinely new and that show you something that you've never seen before. So how do you do clustering in such a way that you can obtain these sources straightforwardly? And in feature extraction, you can do an eigenspectral analysis of VGN and galaxies, whereby you have, for instance, millions of spectra of VGN and galaxies, and you try and find, the best subspectra that represent the whole variety of VGNs and galaxies. For a lot of machine learning work, the Sloan Digital Sky Survey that you might have heard about was groundbreaking. That was because it was a large survey, but it covered a larger chunk of the sky in an homogeneous way, with digital cameras. So it was possible to produce images and to store them in an homogeneous fashion online. But truly, the innovation of the Sloan Digital Sky Survey was in how its data sharing culture was shaped. So they committed from the very beginning to release data regularly. They're now at their 18th, I think, data release. And they released it through a database that allowed you to download sources based on some criteria, and to do so, homogeneously across the full footprint, which covers sort of, 1/3 of the sky or so. So over the years, the so-called SDSS Sky Server, or Sky Server, I think it's called now, was it, by billion of web bits and by, hundreds of millions of external SQL queries. And it has allowed them to try out, a lot of tools that were already available on astronomical data for the first time, because this was the first time when data was made publicly available in a documented and in a easily accessible fashion. So people have done lots of things. They've gone through the classic, classification analysis, regression analysis, and so on and so forth. But truly, the SDSS Data Archive single-handedly spawned what we now call astroinformatics, and it is perhaps one of the best prototypes of big data science exploitation in the 21st century. Now, astronomers are by default, limited only by their capability to process the data in an homogeneous fashion and release it to astronomers and to the public in an homogeneous fashion, and by the time and by the resources that these efforts take. But by and large, I mean, modern telescopes have got image quality, image homogeneity, and size, I mean, that are accessible, I mean, to to most people with a laptop. So there is actually an opportunity to democratize some of these efforts, so that, I mean, students and researchers, I mean, from all over the world can actually access data that would otherwise, I mean, take decades to obtain, or maybe days to transfer over the internet if you wanted to get hold of the full lot. Now, of course, things are going to get trickier over the next few years. The LSST is a case in point. It's an observatory, although, well, it's now being renamed. It's the Vera Rubin Observatory. Again, my slides show their age. It's basically a large telescope that is going to do the ultimate optical transient survey. So it's going to observe with an 8-meter telescope with a 10 square degree field. It's going to be observing all of the southern sky, I mean, about 1,000 times over 10 years. It's going to take a couple of 15-second images over different chunks of the sky in order to be able to compare image number 1 with image number 2, and to see if any source has brightened or darkened in between image number 1 and image number 2. And this will allow people to analyze the data streams in real time and to produce so-called alerts that can be shared with astronomers around the world, so that anybody, I mean, if a supernova or a gamma ray burst happens in the field of view of the LSST, I mean, astronomers will be alerted in real time, and automated telescopes will be able to follow them up in a much more streamlined fashion. So now there are all sorts of agreements, I mean, being made, including with South Africa, so that, I mean, the Sutherland telescopes might be able to follow up, I mean, discoveries made by the LSST in its over its 10-year mission, I mean, to go where no telescope has gone before. Somebody would put it. So the important thing about the LSST, which is based in Chile, it's led by the US, but it's really a worldwide collaboration, is that not unlike the SKA, is based in the southern sky, and share a number of capabilities and science goals with the SKA. It also shares some of the similar data challenges. And I might have a slide about that. So you should think of the LSST as a data churning machine that will generate, I mean, 2 images of 6 gigabytes every 30 seconds for 10 years. From later next year, not late this year anymore, and it will generate something like 1 million transients per night. So those alerts I mentioned will be measured within a matter of 60 seconds by the pipeline, and over the course of one night there will be 1 million variable sources. So how do you make sense of them? How do you prioritize observing them with other telescopes? So that's a problem that has been tackled, I mean, with a number of automated tools that we're trying to test, I mean, before LSST comes online. And at the end of the day, I mean, you will have something like 30 billion sources, most of them stars within our own galaxy, a few billions, and the vast majority will actually be galaxies outside our own Milky Way. So some 30 billion galaxies observed some 30 trillion times over 10 years. So, well, the NCSA is one of the most powerful computer in the US, and 10% of the computing power there will be provided by 2 LSST users. And people across the world, I mean, are scrambling to create data archives and to find ways to transfer small bits of the data so that they can work on their science without having to get hold of the whole lot. And this is also an area of active interest for machine learning, because machine learning is ideally suited to detect noise from real sources. So ideally, you would only like to be able to transfer the data that correspond to real sources. This is, well, probably by now an out-of-date, outlook of what the SKA, I mean, will be. we currently have 64 dishes deployed since 2018 as Meerkat, and the SKA phase 1 will be made up by something like 303,000 dishes. I mean, these timelines are rapidly receding, well, are rapidly getting a bit farther away in time, but we are, well, most of the contracts for the SKA phase 1 have been put, and so over the next 5 years, I mean, we will see it up and running. SKA phase 2, I mean, will be a more costly endeavor. So if anyone's guess, I mean, when we will see that happen. What is clear is that the expansion between 64 dishes to 300, I mean, will increase the bandwidth of the signal to be correlated across the full array by a factor of, well, by a very large factor. I didn't do the math, but I mean, you must be able to correlate, I mean, every dish, I mean, with each other. So the number increases, well, factorial, I think that's the word. So the SKA will allow us, I mean, to study better the nature of gravity, the nature of the dark age at the beginning of the universe, cosmology across the lifetime of the universe, and galaxy and black hole evolution as a function of time. Of course, this will come with non-negligible data challenges. I'm not putting up numbers here because the real challenge is that, well, the data that is in principle, can in principle be obtained from the full SKA setup is so immense that we can't possibly store it or even analyze it all in real time. So a lot of it, I mean, will have to be somehow filtered out, I mean, as corresponding to noise. And quite how we do that in real time, so how we store, stream, filter, and image data coming from the SKA is very much, I mean, work in progress and something that, well, cool data centers will be devoted to. But there are, of course, a number of more science-like challenges, like how do you spot transients in radio timelines that are very complicated and very often affected by radio frequency interference, and how do you do data processing and science analysis for a worldwide collaboration in a distributed manner. IDEA has created its own cloud. I mean, you can federate it with other similar clouds around the world, but you still have the challenge of having to transfer, I mean, petabyte and exabyte of data eventually. So the people are busy working on how this is going to work. Well, by now, I mean, I've already given you a bunch of mind-boggling numbers. I mean, this is a quick summary of where we are with some of the latest projects, well, some of the upcoming projects. Euclid is, for instance, a space mission that is going to launch in July with a SpaceX rocket, actually, and it's meant to produce, I mean, 1 terabyte per day. LSST, I mean, will start next year on the ground and is likely to produce something like 15 terabytes per day. And with SKA phase 1 and phase 2, here I'm putting up, I mean, a very tentative number of 1 petabyte and 1 exabyte per day. So it's something that begs the question of how we're going to, well, if and how we're going to be able to deal with those data and how we are going to make sense of it. But the idea is that this data will be used by thousands of researchers around the world, often running vastly different research projects. So we must find ways, I mean, for people to be able to access hundreds of parameters, I mean, for their favorite astronomical sources, and to enable, well, to tackle new challenges like the automatic processing, the public access, I mean, to people who have contributed to the funding and to the setup of the machine, and also the scheduling of follow-up observations once something interesting goes boom in the night. I mean, and you find something interesting in the SKA data, you want to be able to observe it regularly, I mean, at once. So, conclusions, I mean, before I get on to something, I mean, hopefully a little more practical, is that data fusion and machine learning are essential tools for a new kind of scientist, I mean, which increasingly resemble a data scientist, but not unlike when people had to learn to type their manuscript in LaTeX. I mean, and now we need to be able to to deal, with data, and there are incredibly amount of useful libraries, that you can pick up, with somewhat little effort. Whether it's Python or R or well, the next language of choice for data scientists. And projects like the LSST and the SKA, where South Africa is strongly involved, will really be the places where the future developments will happen, in the context of multi-wavelength astronomy. And well, idea, UCT and South Africa in general is very well placed, to reap the benefits of a new trend in data-driven astronomy, and to make our research more productive. Now, I will show you a couple of things that you can do with SciServer, which is the SDSS database, and I will send you some notes after the lecture so that you can try it out on your own. I will focus on how you can create queries. So basically, you can interrogate a database, to get hold of ground-based with SDSS and space-based WISE datasets. How you can create a multi-wavelength dataset using SQL, and how you can run some simple machine learning algorithms. And I will make an example of the two things that I mentioned earlier. So the source classification. So how can you tell point-like sources into stars, galaxies, and quasars, and how can you estimate the photometric redshift for galaxies and quasars? So the SciServer is a science gateway. It's something that we are busy developing for Relief right now. It basically allows you to have a little dashboard and to have a quick overview of your files, of the groups, of the jobs that you have or not running, and it also allows you to connect it to a bunch of services that are separately available. In particular, the service we're going to focus upon, all of these services are available for free, by signing up on the sciserver.org, and I encourage you to do that and to play something with some of those. We will focus on these cast jobs thing, which allows you to basically search big databases and match them in such a way that you can create a dataset for your own science work. So here a bit of a summary of what SDSS and WISE were. Well, SDSS is still going on, although in a new model. So the original SDSS mission has by now been completed. So SDSS observed in 5 optical bands from about 300 nanometer to 900 nanometer in these 5 bands that are known as UGRIZ, and then took a few million in spectra of individual galaxies so as to study them in better detail. So the observations in photometric mode have detected, many billions of galaxies, I think, whereas only a few million have had an actual spectra associated with it. And that's important because spectra give you, for instance, an accurate redshift that you can use to train machine learning techniques to measure the redshift for sources that do not have a spectra. WISE instead observed from the sky, so it's actually focusing on an area that you can call the mid-infrared, from 3 micron to 30 micron, that cannot be observed from the ground. And it's a telescope that is that is still operating, launched 10 years ago probably, and it's currently operating only in the 2 mid-infrared bands at 3 and 4 micron, because the other ones, were not usable anymore after the telescope ran out of cryogenic gas, gas to keep it cold. So basically, we're only going to be using the so-called WISE band 1 and band 2 in the following. So when you get to SciServer's cast jobs at this link here, I think you might have to sign up in order to carry out your queries, but it's a very quick sign-up procedure. You might then, you will find yourself, exposed to a simple version of the SQL language. I mean, SQL has got lots of dialects. I mean, there are, well, a bunch of cheat sheets online if you want to play with it. But the general idea is rather simple. So you select, I mean, a bunch of parameters. For instance, right ascension and declination, the U, the G, the R, the I, and the Z band, and the spectroscopic redshift from a table that is available within the database. So photo object all is sort of self-explanatory. It's all objects with a photometric image. And then you can match them, I mean, with a bunch of tables. I mean, we don't need to go into the details. Suffice it to say that this basically creates a full set of sources that have got a clean photometry and that have got spectroscopic redshift wording of 0, meaning that the spectroscopic redshift is reliable and the photometry is clean. So I'll send you, well, these over email, I mean, so that you can play with them if you so desire. Once you create an SDSS only dataset, such as this one from one of the recent data releases, year 16, you can then go on and match it, I mean, with other services. In this case, I'm doing it with the All-WISE survey, that is one of the data releases for WISE. And I'm basically taking all the sources that have got a match in between SDSS and WISE. And again, this is, well, these are all of these select in the inner joins, I mean, are SQL technical terms. I mean, they're actually somewhat simple, and I would encourage you, I mean, to look into it. It can be a very powerful tool, and it's how you access most astronomical data these days. But for the sake of our work, I mean, you can also reproduce this, I mean, with a simple script running on LiFo. So in this case, I mean, you can run on the LiFo a limited number of objects. I think the full number of objects of the previous query was many millions. In this case, on the LiFo, you can create the query text, selecting the top number. In this case, it's 50,000 of objects, and download the photometry only for those objects. And then you can create you can use the CastJobs Python tool, I mean, to create a pandas data frame from the query, so that you can then visualize the magnitudes, the class of the source, which can be galaxy, star, or quasar, and then, I mean, some of the subclasses and the redshift were available. So when you do that, you basically can get hold of the full SDSS spectroscopic database, which provides spectra for about 4 million sources. And the spectroscopic pipeline that SDSS produced classifies sources in 3 classes. Star, which is an actual individual star, I mean, somewhere within our own Milky Way galaxy. Galaxy is a star-forming galaxy, so also known as SFG for simplicity. And QSO, again, I mean, here you might, well, by now, I mean, you probably know that quasars and AGNs, I mean, I've got lots of different names. So all of these, I mean, should be taken as, well, namesakes. I mean, that's meaning the same thing, QSO or quasi-stellar object, quasar, active galactic nucleus, AGN. For the purpose of this work, I mean, we're going to use them interchangeably. So the spectroscopic redshifts, of course, can be estimated for distant sources. I mean, they don't make sense much for stars. I mean, for stars, you measure radial velocities. But if you want to use them as cosmological redshift distance estimators, you can only do that for galaxy and QSO classes. So the Sloan pipeline produces the classification and the spectroscopic redshift estimate. And this is the training set that one can use to put the study of astronomical objects on a quantitative basis. In this case, I mean, we're going to use simple machine learning algorithms to do the trick. So for the classification problem, I will, well, this was for the data science students. So you probably got bored by magnitudes. We quickly remind you that the difference between two magnitudes in the AD system is the logarithm, well, is some form of the logarithmic flux ratio of the fluxes measured in the two bands. And here I'm showing you how stars, galaxies, and QSOs are distributed as a function of two colors. So this is a color plot which I took rather randomly, I mean, from the 5 Sloan bands and from the 2 Weiss bands. So I chose R minus I and Z minus Weiss 1 here. So as you can see, the 3 clouds of data points are rather well defined, but they overlap to some extent here. So the general question that machine learning is trying to address is, how do you set boundaries between these 3 clouds of data points in such a way as to maximize, I mean, the likelihood that you can separate stars in red from galaxies in green and QSOs in blue? Of course, this is only one of the visualization that you can use. You can do that with 7 bands. So you need, well, in principle, you would like a 7-dimensional mind so that you can see and draw hyperplanes. I mean, so that you can separate them in multiple dimensions. What a machine learning, somewhat dumb algorithm does is you can take any number of combination of magnitudes, so any combination of colors, and use it in order to train a model using the sources for which we know the classification. And then you can apply this trained model to run on sources that have not been seen. And this is another visualization of how the colors look like. So it shows you basically all the possible combinations of magnitudes, and you see the 3 classes of sources, how they are distributed in this color space. You can also see the full distribution in R band in this case. And so this can be an instructive plot, I mean, to select what are the best colors to use for your machine learning procedures. But again, if you don't have, well, if you have a reasonably sized data set, such as in this case, you can run the full amount of color combinations without a large penalty in computing time. The problem of extracting the best features arises when you have a possible combination of thousands of features and you want to be able to extract them beforehand so that you don't have to run thousands of tests of your machine learning model. So in terms of specific machine learning models that you can use, probably the simplest one is the so-called K, nearest neighbor algorithm, where, I mean, let's think of a 2-dimensional parameter where you have 2 parameters, x1 and x2, measured for a set of circles, for a set of objects. So these objects have already been classified, and they've been classified as class A or class B. So these are known objects. They're part of your knowledge, well, of your ground truth, of your knowledge base. And then you have a star, a red star, that is sitting somewhere between the 2 clouds. Of course, for the sake of convenience here, the 2 clouds are separate, but of course they could overlap to a large extent. Now, the KNN algorithm does take the closest K, in this case, for instance, K of 3 neighbors in this 2-dimensional space, and measures how many objects belong to class A versus class B. So in this case, if you use a K of 3, you will have a majority of purple objects. So this star will be predicted, I mean, to belong to class B. But then again, if you use a K of 6, the situation will rapidly reverse because there are a bunch of yellow objects here, so that you will have a classification that it veers toward the class A, so toward class yellow. And of course, this happens in many multiple dimensions at once. So if you have 10 parameters, if you have 100 parameters, this can compute the Euclidean distance in 100 dimensions. And the nice thing is that it's all done, I mean, by a Python library, so you don't have to, you don't have to worry about anything, but only giving them the different features that you want to use. And well, as most machine learning algorithms. I mean, from the very simple to the most complicated. I mean, this can be used both for classification and regression. Basically, classification is when you have a fixed number of classes. So in this case, it's a binary classification problem. So it can be, well, A or B. But if you have multiple classes, I mean, it's still going to be a discrete set of classes. For regression, you need to apply regression when you have a continuous distribution of the parameter, like, for instance, the topological hashes that can go from 0 to, well, infinity. And in that case, I mean, you use the regression algorithm to do that. So this is somewhat graphical representation of the k-nearest neighbor. Here you have a little, well, is it only 3? Yes, we got 3 classes, which so not unlike the case that we are having. It is still represented in 2 dimensions. So here I'm showing different areas where a source can fall and be classified as green, red, and blue. So you can get a feeling that in 2 dimensions it all makes sense. Of course, visualizing things in multiple dimensions is tricky, and in order to interpret your results, you might have to go back to the previous post where you show all of the different features and what are the most relevant. But you can often, I mean, go down 2 dimensions and try and see, I mean, if your results make sense. And this is an alternative visualization, which I can't quite figure out. Okay, so let's forget about that. Okay, I forget what that's about, but that's probably a refinement of the previous image that now we don't see. Right. A second very simple algorithm is the so-called random forest, which is based on the basic concept of binary decision trees. So if you have a bunch of data that are classified as 0 and 1 that are sitting between, well, that are distributed in a 2-dimensional space. Again, this is called simply x1 and x2 for convenience. The random forest algorithm tries to find the best line that separates the different classes. So in this case, you can try and run many multiple lines between the dots. So you can run any number of lines. The random forest algorithm runs a bunch of lines and then tries to take the optimal one. So in this case, the optimal one turns out to be this line indicated as 1 that runs through here, because it separates only ones at the top from mixed numbers at the bottom. Then once you have drawn this line 1, I mean, that classifies the ones at the top as ones, you can draw line number 2. I mean, there is no there is no better line, and you can still you've still got mixed values, I mean, of ones and zeros, and then eventually with line number 3, I mean, you separate them all. So this is very simply put, I mean, how, well, binary decision trees and random forests work. Basically, you try and draw a line or an hyperplane in a multidimensional space in order to divide the best way you can data belonging to different classes in, well, step by step. So the first line of the first binary decision tree will be the one that differentiates as best as you can, I mean, the objects. And going forward, I mean, once you have drawn the first line, I mean, all of the other ones, I mean, fall in rapid succession as a function of how well, I mean, you can separate the two, well, the two classes in this case, or the multiple classes that you've got. The classification performance is, well, for binary concepts, can be explained as true or false, but or positive and negative. It can also be generalized to the case of multiple classes and labels. So this is an illustration of what happens when you have 10 classes or so, and you can clearly see that the true positive are the ones that stay along the diagonal, as I showed you earlier. And then the other ones are, well, false positive, false negatives, true negatives, so on and so forth. The general idea is that that you should think about is that is the example of the spam filtering. I mean, where spam filter, I mean, tries to guess whether a source, whether an email is spam, and is trained on some set of spams, on some set of spam emails that is constantly updated. I mean, by the sources that you put, sorry, by the emails that you put in the spam filter. So if the predicted class for a source in the spam filter is spam, and you actually confirm the spam, this is going to be a true positive, and similarly, I mean, for the other classes. So the key thing is that this can be extended to multiple classes. I mean, by using this table here. I mean, where the true positives are only the ones sitting on the diagonal, and the other the sources, I mean, sitting outside, I mean, diagonal, are classified as well as those three other classes. I mean, as shown here. For the Sloan sample that I showed you ahead, I mean, that you can generate, I mean, with a simple query on Sky Server. This is what, I mean, the confusion matrix looks like. Again, I mean, predicted label and true label. So these are true galaxies. So out of the true galaxies, 50,000, I mean, are classified correctly. 700 are classified wrongly as stars, and 400 are classified as QSOs. And well, similarly, somewhat, I mean, for the other classes of objects. This is not too bad, and you can actually write the confusion matrix in percentage form, but here I'm doing it in a slightly more accurate manner. So here I define the three or four ways in which you can classify, in which you can measure the performance. One is the precision, which, well, astronomers mostly call reliability, but in machine learning, it's almost invariably referred to as precision. So it's good to keep that in mind. Recall instead is the completeness. So how many of the real sources, I mean, you actually pick up. And F1 score is a combination of precision and recall. And accuracy is a slightly different definition that tries, I mean, to bring together both precision and recall. So these are useful terms to bear in mind. I mean, when you read any machine learning paper, although astronomers try to bridge the gap and use more astronomically classic terms, I mean, these are almost invariably better to use because they're precisely defined. So the general idea is that once you know where the objects fall in the confusion matrix, you can measure the number of true positives, true negatives, and so on and so forth, and you can measure these four parameters and have an estimate of the overall accuracy. As you can see here, I mean, the F1 score, which for simplicity we use as a summary of the goodness of our performance, is always at about the 90% level. It is a little better for galaxies that are less controversial. Stars and quasars often get mixed up with each other. If you take a look at the confusion matrix earlier, you will see that, so that the performance is slightly worse. And on average, I mean, the classification performance is 95%, which means that 95% of the times, I mean, we are classifying sources correctly, which is a good start, if you ask me. Second problem is the regression, and the problem of the regression is basically based on the fact that using a couple, again, of random combination of colors, I mean, that I chose just for convenience, you can see that the redshift shown by the color bar rapidly changes as a function of color. So in this case, these are galaxies, and galaxies with redshift 0 are here, whereas galaxies with redshift 4.5, I mean, are up here. QSOs note that they spread a very large redshift range because QSOs are much brighter, so they can be seen at very large distances. QSOs have got a similar behavior, although it's a bit more intricate, perhaps even because it's turns around a little bit. But again, this is only just a random combination of colors. In practice, I mean, the machine learning algorithms are set up so that they can combine any combination of features that you give them. Astronomers like to use colors because they are used to them and they can interpret them better. But there are also studies where you can extract the best features, from your data set without any input by the astronomers. That only makes it a little bit more difficult to interpret, but it has often the power, to increase the accuracy on the whole. How do you measure the performance of a regression? In this case, it is a one-dimensional quantity. So we want to measure the photometric redshift as a function. Sorry, we want to measure the photometric redshift, and we want it to be as close as possible to the spectroscopic redshift. So the ideal is a one-to-one line, with a very thin distribution. This is what it looks like, for galaxies after you train the algorithm very well. Here you have a density, so you see that there is a large density of sources at about redshift 0.1, 2.2, so that allows you to be very accurate here. And then the spread gets a little larger. When you go to higher redshifts because the training set is a bit smaller there, and also the quality of the photometry at higher redshifts is smaller because it is more difficult to measure the distant object. It is more difficult to measure the faint objects. But by and large, you can measure the normalized MED. I will get on that later, or the RMS. In order to see how close the photometric redshift resembles the true spectroscopic redshift. For QSOs, the plot is the same. You might note that both the NMAD and the RMS are substantially larger for QSOs than they are for galaxies, and there's a reason for that. But this is how you quantify the actual performance. You measure the normalized photometric redshift error, which is the difference between the predicted photometric redshift and the true spectroscopic redshift, and you divide it by 1 plus Z-spec in order to normalize it so that close and distant sources are put somewhat on the same scale. And here is what I refer to as NMAD, or normalized median absolute deviation. This is a bit of a, weird statistical technicality, but you can look up, the median absolute deviation. The general idea is that if the distribution of errors is Gaussian, if the distribution of error is Gaussian, MMAD and RMS should be exactly the same. If the distribution is not Gaussian because you have a large number of outliers, so sources that are far away from the one-to-one relation, the NMAD will be a measure of the typical error of an individual source, but the RMS will be larger because it will be affected by the outliers. And here you can see an example of what I mean. So for star-forming galaxies, for instance, the NMAD is about 2%, which means that you can, for an average source, you can predict the number, the photometric redshift with an accuracy of 2%. But there are 0.6% of the sources where the error is more than 15%. So these sources are so-called catastrophic outliers, and they cause the difference between the NMAD and the RMS. So the RMS is larger because the distribution is not Gaussian, because we have a much larger than we have a much larger number of outliers compared to the Gaussian distribution. This gets even more interesting for AGNs because AGNs are pretty tricky. You have about 18% of them that have got an error of more than 15% in redshift, and this creates the large difference between the NMAD and the RMS. So the NMAD is 5% for the AGNs, whereas it is 20%, whereas the RMS is 20%. So those are useful quantities to keep in mind even when you compute different statistical techniques, different statistical quantities in astronomy, because very often we always assume that everything is Gaussian, whereas it's very often not the case. So comparing the two is a very useful tool in a number of analyses. And this is a short, a visual illustration of why it is subtly more difficult to find photometric redshifts to measure photometric redshifts for AGNs than it is for star-forming galaxies. The classic SEDs of star-forming galaxies are shown by solid lines. So all these solid light lines are star-forming galaxies. And the important thing to bear in mind is that you see that here at short wavelengths, there is a huge difference of SEDs, which means that, and the SEDs go, start from a very low point, go to the top, and then decline again. So this means that there are lots of peaks and lots of features, lots of spectral features that you can use to anchor the photometric redshift measurement. So if you move them to the right or to the left, as a function of redshift, you will be able, to tell, whether this SED is shifted or not. But bear in mind that the AGNs are instead shown by the dotted line, and these are very flat as a rule. So this means that, not unlike with the radio continuum spectrum, it's often very difficult, to measure the redshift if you shift the SEDs to the left or to the right, because they are not, they're a bit featureless. So they don't show large peaks, large troughs, and this makes it substantially different to work with the AGNs. And observational astronomers have known that for quite a long time, because very often when you have an AGN, your only option is to take a spectrum, because then you can actually measure the very peaked emission lines that are shown here, which are the only features that you can rely upon to measure a good redshift for AGNs. And yes, I think that's the last slide. I will leave you with a couple of useful resources that you want to check out. Depending on your language of choice. Astronomy was rather popular a few years back. I think these days, sklearn should really replace it. So strike that. Have a look at scikit-learn if you have a minute. You will find lots of useful tricks. To do your statistical work for you. Our packages, for astrostatistics are also available, and provided as part of a book that should also be available in the library for those who are keen on R. And there are at least a couple of very useful collaborative platforms, that provide science gateways where you can access lots of astronomical data using SQL, importing them into Panda data frames or into Python data structures, and then play with machine learning techniques or with visualization techniques in order to see what your sample looks like. And I think here are perhaps some of the very links where I took a look, where I took some of the information to describe the k-nearest neighbors and the random forest algorithms in Python. More in general, there's a huge literature. I forgot to add that to the slide. I might do that before I circulate the number of machine learning papers in the astronomy journals that have been published over the last year is more than since records started 20 years ago. So this is all rapidly getting bigger, and so it is certainly a good time to become involved and to spend a little time looking at some of these tools, because very often they will make your life simpler, even with with somewhat more trivial astronomical problems or statistical problems in different respects. And I am done here. So